Okay, so thank you everyone for attending the seminar. Today we have the pleasure of having Dr. Miguel P. Encinar. He has a PhD from the aerospace engineering at the Universidad Politécnica de Madrid under the supervision of Professor Jiménez. So of course he did his PhD in turbulence, and he has now been working in turbulence as a postdoc and currently too. He went to the US at the Johns Hopkins University for a postdoctoral position, and currently he's a professor at the Carlos III, the University of Madrid. So he has made like very large simulations of turbulent flows and very small ones, and he's been trying to ensemble these small simulations and having a generalized representative, view of turbulence. And well, today he will present the computer-aided discovery of significant structures in isotropic turbulence. So once again, Miguel, thank you very much for accepting our invitation. And well, you can start when you're ready.
Well, thank you, Bernard, for the introduction. And I would like to thank you and Oriol, who's not here because he couldn't come, for thinking of me for the seminar series. It was a pleasure to come here today. So, well, this is work that I did with Professor Jimenez during my postdoc with him after my PhD. The founding of this is part of an ERC of Jimenez, and I have to acknowledge the UPM because I was there when I was doing this research, and then the Carlos III University, which is where I'm now. And before starting, I would like to introduce a little bit this part, the large-scale computational fluid dynamics. I think that this talk is interesting for this seminar series because typically we have been doing very, very large simulations, which is the thing that people have in mind when they hear these words. For a very long time, we have been doing that. And now Jimenez has switched to doing this other thing, and this happened in the group, and I also feel that is a very interesting approach that now is possible to go through, with the new GPUs, which are graphical processing units. And what we're doing now, as Bernard introduced, is instead of doing one very large simulation, we are doing many, many small simulations. And I hope I will convince you through this talk that this is an interesting way of approaching the problem of fluid. So what's the background for this work? The idea is that we want to study turbulence from a structural point of view, which are the turbulent eddies that control the dynamics of the flow. This is something that has been done for a long while. But the idea is that we would like to stay as free from bias as possible. So typically what you do is that you observe the equations, you decide that some terms look nice to you based on various reasons, and you decide to construct eddies from those quantities, and you study those eddies. So what we would like to do is the opposite. Let's try to see which eddies are interesting, and then we will study them. And this is what this is about, okay? So this methodology, which has been labeled by Professor Jimenez as Monte Carlo science, has been proposed in a series of papers by him in which he manipulates 2D turbulence. By looking at Jimenez and Monte Carlo, you can search for them. And he tries to infer some dynamics of the flow quite successfully into the turbulence using this method. And the present work tries to extend this to three-dimensional turbulence, which is it has a series of challenges associated to that dimension leap. So I'm going to summarize this method. The idea is that you have a turbulent flow, and in case that you don't do turbulence and you still are here, and you have any other problem with many degrees of freedom, this method is general. You don't need to have a turbulent flow for this. If you have anything that is sensitive to initial conditions, you are doing an LES of a plane, you're doing a boat, it doesn't have to be fluid mechanics, you have a network with many degrees of freedom, there is a chance that this still works for you. So what you're going to do with this dynamical system is that you're going to test actions that are local in the space of interest. In our case, this is the physical space. We're going to try to poke the flow in very particular places. And what we're going to do is we are going to track the sensitivity of those places to these perturbations. And we are going to see if they grow a lot or a little. For that, you have to define a norm. We will talk a little bit about that. And once you have doing this, you will get a series of places where the flow is very sensitive and a series of places where the flow is not sensitive. And well, the task that you have at hand now is some sort of a classification problem. You need to try to get some sense of why some places are sensitive and why not, with the hope that that tells you something about the flow dynamics. So the rest of the talk, I'm going to explain how we apply this to 3D turbulence and what we learn from this. And I hope I convince you that this is useful. So all the contents of this talk, or maybe 90-something% of them, are in this EFM paper that came out earlier this year. So if you have more questions, you can check it there. So this is the flow of interest. I told you, I advanced you that I'm doing a small problem. The problem is decaying homogeneous isotropic turbulence. This is a triply periodic box. So it's the easiest way of computing turbulence that you can think of. And the number of grid points is 256 cubed. This gives you about 5 million degrees of freedom, which is significant, but is small for a simulation. Typically, the simulations that you run in a cluster or in a praise call or something like that, they are 5 billion or 50 billion degrees of freedom, so are much larger things. So this, compared to that, this is small, okay? This is the resolution, which for isotropic turbulence, it depends on the dissipative scale, which is very tight. It's not very good, but but it's enough to reproduce everything in the flows. Because we care about the inertial range, this is not very important for us. And the only thing that you need to know is that these filaments, which are the dissipative structures, should be well reproduced. And based on the picture, we have metrics on that, of course, but it's well resolved. And this tight resolution, we're using it because it gives us a nice Reynolds number. In isotropic turbulence, Reynolds number is the ability to separate the energy scales, which are in blue, from the dissipative scales, which are in red. So the difference between the size of these big, large blue things and these small red things is the Reynolds number. And in principle, we want those to be separated because the things that we're studying, which are the inertial range, are in the middle. So in order to have middle, we need them to be far away. So this case is selected because it's large enough to be useful. This is a useful problem. It has a large enough Reynolds number to have inertial range, but this is still affordable because it's a 256 cube. So in this flow, what we're going to do now is introduce those perturbations. For that, we're doing it in a quite simple way. We're taking a Gaussian of a given size. This automatically means that we have introduced a size to the problem. We're multiplying that Gaussian to the velocity field. This, of course, doesn't satisfy Navier-Stokes equation, so you have to do something about that. And then you project them into the space that satisfies continuity, and you get something like that. So it's a Gaussian that you have multiplied by the velocity field and gives you something that is very, very small, located in a place. It has a given size. And what you're going to do now with this tiny perturbation is subtract it from the velocity field. When you do that, you get something that looks almost the same, but in that piece there, rounded in yellow, you have subtracted a little bit. And what you're going to try to do now with this is you're going to run this simulation in time and see what happens with it. It may seem obvious because of what we know about turbulence and that perturbations grow because it's a chaotic system and so on. But I promise you that the answer is not obvious. I'm going to give you an example. This is a real case. Here I am plotting two perturbations at the same time, but this is just for plotting. These perturbations are two separate simulations, okay? One for the red perturbation, one for the blue perturbation. These are two places in which when you stop the velocity of the flow, in the blue case, you're removing 40% more velocity, about twice the energy than in the red case, okay? So one could expect that because you are introducing a larger perturbation, it's going to harm the flow more, but then you run the simulation in time and you find that it does not. It's the complete opposite. So the red perturbation outclasses the blue perturbation, grows 13 times more. So if you think about now, after some time, it's 9 times larger than the blue perturbation. And that means that it has grown 13 times more because initially it was weaker. So it's not obvious a priori without running Navier-Stokes equations, which perturbations are going to grow more and which ones are going to grow less. And this is the type of thing that we want to have a model for, okay? And here, with this silly example, I have introduced three things that are important. One is how you define growing. There are two ways. One is this 9, which is how strong are the perturbations after some time. Another one is that 13, which is that this one outgrew by 13 times faster the blue one. And another thing that I introduce is this time parameter, that there is some time horizon that you have to observe the perturbations, because if I wait infinite times, both of them will be equal, okay? So now in the first part of the presentation, we're going to go through these three parameters, how we decide how to select them. Also, we would like to test every possible perturbation that one can imagine, but that's impossible computationally, but at least we want to test a few. We try to include more, but at the end, this is computationally very expensive, so we decided to do only 2. One is the one that I just explained. You're removing some kinetic energy from the flow, and if you project the equations over the gradient space, you can create equations for the vorticity, and then you can do the same game, but removing the entropy. And with this, we're hoping to, I will talk a little bit about both in the talk. We're hoping to cover all the space and not leaving anything behind. Most of the time I will talk about the energy, but if I said so, it will be, we will use some of the results from the entropy perturbations to validate what we get from these ones. And this I advanced it already. You can measure the 9, which is how much things are after some time, or you can measure how much times amplify at a time, which was the 13. And this will be important because the problem of measuring the absolute growth is that you are also considering how much energy you're putting into the system. So the same thing, we are using both norms. Ideally, you would like to have more, but 2 is as much as we can do. And we're using this to validate each other. So results that are robust for all the 4 things that I talk about will be the ones that we're considering to be important. And then you need to test several sizes, because in turbulence, everything depends on the scales. So what we have done, the first line is the integral scale. In terms of the integral scale, the bottom line is in terms of the dissipative scale, and we have sampled 7 different sizes. We have 1 in the dissipative range. This is very dissipative. We have something on the inertial range, very large, the energy containing scales, and everything else is somewhere in the inertial range. And for this, most of the results for the inertial range are similar. So for this tag, most of the time, if I don't say anything, I'm showing this one, which is the one that is in the center of the inertial range and works very well. Also, you have to do some compromise about where you introduce your perturbations. You could randomize this, try to put them in, because you cannot try every possible place to introduce these spheres. And instead of doing it random, we decide to do a grid as thin as possible, but at the end we have to leave some gaps, and this is the scheme that we choose. By doing all this, all the perturbation types, all the sizes, the norms, and the fact that you need to test many initial conditions, because turbulence is sensible to the initial conditions, so you need to test many cases. You end up with the fact that, and you need the statistics, so you have to do many trials of it. You need to run many simulations. So for example, for this case, the fourth case, only 1 perturbation type, we have to run 80,000 simulations in order to have statistics. And this is that we take the initial conditions for these independent initial conditions for simulations that are steady state in order to keep them statistically independent. So with all in all, we had to run for this work about 1 million simulations, okay? And because this was about large scale simulation, I added this line. So the only reason we could do this, afford to do 1 million simulations for this case, is because we set up a code that runs the simulations in a GPU. The GPU is very fast at running the simulation with the perturbation and so on, but this wasn't fast enough. because when you run 1 million simulations, you also have the problem of what do you do with the data that you're generating. So what we did is that we packed this GPU routine into a Python code that is asynchronous and leverages all the post-processing to the CPU. So what we are doing is that we're doing the computations, computing the statistics, and throwing away the raw DNS data, because otherwise there is no way to handle for us 1 million simulations. And I believe based, for example, Bernard, I know Bernard has a code that is similar to this, that a lot of people is for reinforcement learning and other tasks that look similar to this. You have to run many simulations and you have to do something with the data. Are running strategies like this that are very efficient because you are using 100% of the GPU and 100% of your CPUs. Because otherwise, with a GPU code, all the CPUs of your node that you got hours for are useless because you're not using them. So in this case, we use this strategy to utilize the resources as good as possible. So let me talk, even if this talk is about the flow and not about the perturbations. I have been trying to study this now. Let me give you a few details about them because it's necessary for the problem. Okay, and remember that I will talk more about extreme perturbations because we only care about the things that either grow a lot or grow a little bit. So the first thing that we need to do is decide the time scales of the problem. We know that that's important, and that's what we get from this. And also if things, some sense of if things grow a lot or a little. So what you have here is the growth of the perturbation. This is the perturbed field minus the original field to the square. So this is the energy of the perturbation for a few test cases that run for very long time. This is 300 turnover. This is very, very long time, okay? In order to assess how are the scales of the flow. And you see that the perturbations grow, but one thing that you can notice immediately for the blue one is that at some point the perturbation stops to grow. And that's counterintuitive. So what's happening is that the flow is decaying itself. So it's not that the perturbation is growing, it's that the flow is decaying. And this seems that the perturbation is dissipating. But when you compensate the energy of the perturbation with the energy that you have in the flow field, the perturbation is still growing. Okay, so the first thing that we have to realize is that because we have a decaying flow, we need to compensate every measure of energy that we do with the energy of the base simulation, because otherwise you may decide wrong if something is larger or smaller. And the second one that is to make sense of the time scales is that the time scale is changing for the same reason, because the turbulence is decaying. And the way that you construct a time scale is from the kinetic energy and the integral scale. And these things are changing with time because of the decaying of the flow. The time scale that you get from these two is changing. So the other thing that you need to do is absorb this into a time scale and produce this normalized time. And when you put everything in these two units, everything makes more or less sense and matches what you could expect for the growth of a regular perturbation in a steady state. They grow more or less exponentially, at least initially, and they tend to asymptotic. So if I don't say anything, the time is always normalized like this, and the kinetic energy is always normalized like that. And if it's entropy, I will normalize it the same with the ones of the base flow. And when you do that with the mean perturbation growth for different sizes, you get something like this. This is if you evaluate the absolute norm, which is what we said, this thing is 9 after some time. And this is what happens when you evaluate the relative norm, okay? Which is this thing grew 13-fold, which is different. And you can see that the behavior that you get from size is the opposite. Large perturbation size grows in this direction. So large perturbations start big and keep big, but just because they started big. And small perturbations start very weak, but they grow a lot. So when you look at the amplifications, the order is reversed. And this will have this initial difference is only proportional to the energy that you introduce, which is proportional to the volume of the perturbation. So there is no information here from the dynamics of the flow. It's something artificial that you're imposing on the simulation. So We also learn from this that there is an initial time that is not here that you have to remove from your statistics that depends from the size. And as I said, that is, small perturbations grow more, even though after any time they never grew as much as to catch up to larger simulations. And with these two things, we are able to compare one size to the other. And the other thing that we care about is how do we define the time scales, the time to define if something is important or not. And for something, what we're going to do is to compute the same statistics, but for extreme perturbation. So what you have here is the average, but only for the 5% stronger perturbations. And here you have the average, but only for the 5% weaker. And again, you can define this. In the top row is defining an absolute sense. This is something after some time. And in the bottom panels, you have the amplification. That's why in the origin, in the bottom panel, you always have one, okay? And what you have in the left is the quotient between the two, the ratio between, in this case, the amplification of the top 5% and the bottom 5%, and in this case, of the absolute norm of the top 5% against the bottom. And why this quantity is important, and we're going to use this quantity as our definition of significance, is because of the following reasoning. What we are trying to do is being able to predict if something grows a lot or a little, being able to, based on the flow, classify those two events. So the more different these two things are, the easier it will be to tell them apart. In fact, for the for the large scales, which are in purple, this quantity is approximately 1, which is this purple line. And this already told us that there is no way of classifying this. If two things, the ones that grow a lot and the ones that grow a little, are the same almost, the growth is the same, there is no way to tell them apart. And the opposite is true for the dissipative range. This is something that is easier to tell apart because the difference between the things that grow a lot and the ones that grow a little is 12-fold. So there is a huge difference of events here. And this also gave us the time horizon at which we have to look at, which is the one that makes our life easier. There is a time in which these two things are most different, which is the maximum of this curve. So in order to define if something grew a lot or grew a little, we are looking, depending on the site, at a different, and depending on the norm, at a different time horizon. So with this, we have already everything we need. We have, if something grew a lot or a little, we have the time at which we have to look at, and we have the sizes at which we need to look at. And what we can do now is look at the properties of the flow, which is the idea of this is to have a sense on which parts of the flow are more affected by perturbations and which. So what we're trying to do now is see if we can decide without running the DNS if a perturbation will grow a lot or a little. The idea is simple. I can always do that by running a DNS, but a DNS is expensive. There is something I can measure at the flow and why that something is related to the perturbations that allows me to predict if something will grow a lot or not without running the simulation. So the way we have approached that is as a classifying problem. If I'm able to measure something on my flow that classifies my future growth, in principle, it should be related to the dynamics. And for that, we have tried to do it in an automated way. We have defined it up to 40 quantities. The quantities are something that looks like this. I'm going to explain this example and then we will go through the rest. This bar operator is multiplying by the Gaussian. So if you think about it, that is isolating whichever quantity I'm multiplying by the Gaussian to the region where I'm introducing the perturbation, and this is taking the average. So this, for example, is the velocity vector. This is the multiplying by the Gaussian, and this is taking the average, more or less. Then the notation is a little bit, it's not exact, but it's more or less. So this is the mean velocity in the region where I introduce the perturbation. So in principle, if convection is important, this could tell me if I'm able to, if something is going to be significant or not. This, which is I take the square first before doing the average, is the kinetic energy in that region. So if the kinetic energy in that region is important, this should tell me, should be able to classify if some things are going to grow a lot or not. This is not exactly the same because of the support of the Gaussian. We kept it as a sanity check and it turned out okay. And this is a square power, a fourth power that we take to see if intermittency plays a role. Because our Reynolds number is limited, if it would have been a problem if this was more relevant than the square, but it also turned out okay and it's not very important. So these two, you can ignore them, that they are sanity checks all the time. And the rest of the classifiers look like this. This is the mean rate of rotation. This is the entropy. This is the square of the rate of strain tensor, which is the dissipation. This is the mean stretching field. This is a tensor, so it has eigenvalues. These eigenvalues are important for turbulence theory because they tell you if the flow is locally stretching, contracting, or so. So we also keep track of them. This A thing is this tensor, is used to identify vortex seeds. So in principle, this should be important, more important than omega and S if there is a vortex seed structure in that region. And again, it has eigenvalues. Q and R are the two invariants of the velocity gradient tensor. They also inform you about the topology of the flow in that region. So again, if the topology is important, these should come out as good classifiers. And these are the time evolution of gradient terms. So this is producing a strain, rate of strain, and this thing here is producing vorticities, the vortex stretching. So in principle, if you are generating new gradients, this should be important. And finally, this two is what we did to the flow. This is the kinetic energy that we introduced to the flow when we did the perturbation. And this is the entropy that we introduced to the flow when introducing the perturbations. And again, there are sanity checks, but they turn out okay. So in principle, with this, we wanted to be able to cover all things that we thought reasonable that could come out as important. And now you have to classify somehow if these things can predict the significance or not. And in order to do that, we're using something called a support vector machine. Maybe someone has here in the audience has used them before. The idea of a support vector machine is illustrated here for one dimension and it's very simple. And the idea is if you have the probability density function of a magnitude A, and you condition it in orange to be insignificant and in blue to be insignificant, this is grow a lot, grow a little. If you are able to draw an hyperplane, which in 1D is a line that separates these two entities, this means that by knowing A, you can already tell a priori if this is going to be significant or not. But if you're in this scenario, for example, you know B, it decreases your uncertainty very little. So you could may as well take a random guess. So a support vector machine tries to first find this hyperplane, and then it gives you a score of how good this hyperplane is at separating these probability density functions. So for A, it would give a score close to 1 because it's a very good classifier. And for B, it would give you a score close to 0, okay? And what I'm going to show now is result for this for the 40 classifiers that I have talked about. Here I'm only showing one-dimensional support vector machines. In the publication, you also have the result for 2 and I believe 3-dimensional, if you're curious about it, but with 1D is enough to understand the problem in general. So this is what you get. In blue, you have the blue dots are in the diagonal, and they are the score using the absolute norm and the score using the absolute norm. So they always fall in the diagonal, and the idea is that you can use them as reference for the green points, which are the score using the absolute norm and the score using the relative norm. So this is the amplification, how much things grow, and this is how much things are at the end. And the idea is that if, for example, here, this is a case, if green is below blue, it automatically means that removing the initial magnitude of the perturbation changes the score a lot. So the second thing that you see in this plot is that points are not isolated, they appear in clusters. There's a cluster here, another cluster that has 2 subclusters there, another cluster there, and so on. And these clusters belong to different groups that more or less represent the same of the 40 classifiers that I saw before. So for this talk, we can simplify them to two clusters. The one that has Q squared is the kinetic energy, and the one that has gradient squared is everything that has to do with gradients. Here you have the first invariant square of the velocity gradient tensor. You have the entropy, you have the dissipation, and all those terms, okay? You have the vortex sheets too. So what you see is that this gives you reasonable classifying power, 0.7 score. The energy gives you better for the inertial range. But when you are looking at the amplification, if instead of wanting to predict all the final value, you want to predict the amplification, the gradients are still equally good. Some of them improve a little bit, some of them worsen a little bit, but they are in the same place. Whereas the kinetic energy, all of a sudden, is useless. And this happens for all the scales. Okay? And the gradients stay the same. For large scales, things that are closer to the inertial range, the kinetic energy is a score of 1, essentially. You can always guess the value by just looking at the kinetic energy of the region of the flow that you're perturbing, and the gradients are low, are worse. But this effect that when you look at the amplification, this one lower a little bit, but they stay the same, and this one's lower a lot, it stays the same. And when you look at this dissipative range, it's like a mirror image of the large scale, right? Notice that kinetic energy is no longer a score of 1, it's something like 0.9, and gradients are better even, they are close to 0.8. And when you look at the amplification, not only they are still good, but they are even better. So in general, gradients don't have the best score, but they are consistent across both norms, and for all sizes are reasonable. And when you look at what happens with perturbations that manipulate the vorticity, you get the same. So kinetic energy is always bad, and gradients are always good. And when you are looking at the amplification instead of about the absolute norm of the gradients, they are still in the range of 0.6, 0.8, 0.7. So gradients are classifiers that are always good for all the 4 cases that we said that we were looking for. And kinetic energy or other things only work sometimes. So we're going to focus on why some gradients are able to classify and why not. And for that, what we're going to do is look at the flow. We know that we have to look at the gradients and how they interact among themselves, but the flow looks like this. These are cases that in this code, every time I find something that is significant or insignificant, I take the flow field and save that particular piece to see how the flow looks like. And they look like this. So whenever you have a significant structure, looks something like that. Entropy is plotted in red, so it's like a tangle of vortices. And insignificance looks like this. The fact that this is large and this is small, and that this is very complicated and this is simpler, has to do with the geometry of that particular region, because the thresholds for this plot are chosen by percolation, which is purely a geometrical algorithm. So it has nothing to do with the fact that this is more intense or so on. So what I want to try to do now is see if I can get something in common from all these things that is related to the gradients that I already know, and something in common to all of this that is also related to the gradients, to see if we can improve our knowledge from what we already know. And the first thing that one can think of computing is a conditional average, which is how the flow looks on average on those points. For that, you need to, because the flow is isotropic, you need to select principal axis. And what we're going to do is pretty standard. We're selecting the principal axis of the strain. And another thing that one has to notice by looking at this video and trying to compute a conditional average is that no matter how good you are at aligning with those axes, the average cannot be representative of all the details of the individual structures. So something else needs to be done. So I'm going to go, I don't want to be very long. These are the conditional average. You have to align one which is with each direction of the strain. They look like this. They always look, this is the most compressive, but they always look like one vortex, and that is close to a straining structure. What I want to point out is that if you look at the vorticity and strain, they are in very different proportion for the insignificant and the significance, okay? In the insignificance, the vorticity blob is much larger than in the significant. And in this case, there is not even a strain blob. The thresholds are the same in every case, okay? So, and here you have a large one. If you move to the intermediate, you can see also this difference of proportion. Here, the strain is larger than the vorticity, and here they are comparable, or even the vorticity is larger than the strain. And if you go to the most stretching, is even more pronounced. The strain here is enormous. Everything is dominated by the strain. And here, everything is dominated by the vorticity, okay? And I told you this doesn't tell you the whole story. You don't need to rely on mean statistics to classify this. For example, this is just one silly example. If you look at all the significance and want to measure this tangle of vortices, if it's more complicated in the case of the significance than in the insignificant, you can compute the fractal dimension, also known as the box counting dimension. And when you compute them for the significant ones and for the insignificant ones, you get very different numbers. Okay, the significance look like a tangle of worms, which is this fractal dimension of 1.4, and the insignificance look like a tangle, something that is flatter, like a surface or something like that. So in principle, you can tell them apart just from geometrical arguments, or as we saw in the previous slide, from the balance between strain and vorticity. So for this last case, the balance of the strain and vorticity, but the last thing I'm going to talk about is to try to convince you that this is relevant, because so far it means it thinks that I have looked at many things, and we don't know if it's useful or not. When I was doing this, I was thinking the same thing that you're thinking now, that maybe everything is useless. So I decided to try this. And this is called a nudging or a simulation experiment. And I'm going to try to use this to convince you that the things that we learn from the flow are useful. And how this works, this experiment works, is I have a base simulation. This could be, in this case, is the flow I have studied, but this could be anything else. And it's forced. This is doing its own dynamics. And I'm not doing anything to this guy. I'm going to call it A. The only thing I'm doing to it is plotted in orange and blue, is that I'm going to find 10% of the volume where this magnitude, which is the second invariant, which is the difference between the entropy and the strain, is either negative or positive. Why I'm doing this? Because I know from the conditionals that I just showed you that in places where the vorticity dominates over the strain, this thing is insignificant, and in places where the strain dominates over the vorticity, this is significant. I'm not going to compute the significance. For that, I have to run Navier-Stokes. I'm just measuring this quantity, filtering it at the size of the perturbation, and finding the 10% of the volume. This is something that is extremely cheap to do. It's something that I can do every time step of my simulation. I'm finding this. And what I'm going to do now is that I'm going to run two subjugate simulations. In one, I'm going to feed it the data in the places that I think that they are insignificant for the dynamics. And to the other one, I'm going to feed it in the places that I believe are significant. So the idea is that if it's true that this thing that we found as relevant for the dynamics is relevant, I should find a difference between these two. These two, the only energy input that they have, which is the same for both in magnitude, is 10% of the energy of the base simulation A. So now you run these two in time, you run for a long time to make sure that this doesn't depend on any transient, and you find this. So for the places where you are assimilating, for the simulation where you are assimilating in places that you think they are insignificant, you get about 80% error compared to the base simulation. Consider that the maximum of this curve is 90 because you are assimilating 10% of the volume. So that for sure is correct. So you are getting an extra bit. That 10% of the volume that you are assimilating is affecting another about 10% of the volume in terms of dynamics, and it's lowering this line up to 80%. But for the significant cases, this is below 50, something like 45. So by assimilating only 10% of the volume, you're affecting about 50% of your domain of the simulation. So, and the difference between these two is 60%. So if you care about read data from some places to do an assimilation or those type of algorithms, or you're trying to do a forcing, or you're trying to do control, knowing which places the flow is more sensitive to, in this case, assimilating data is important, okay? And with this, well, I have gone through these conclusions through the tags, so we don't need to go through them. I can leave them for you to read and ask any question. And I would like to thank all of you for coming and listening. As said, I'll be happy to take any questions from the audience.